Okay, now we're going to take and combine two problems we've already done, namely a block on a ramp, but also two blocks attached together over a pulley. So here we're going to have one block sitting on a ramp, and for simplicity's sake, we will take the surface to be frictionless. And a second block hung over the end of a pulley, and this will be allowed to fall. Here we're going to give specific values for the masses and the angles, and we'll say the second block right here, the red one, is a certain height above the ground. And again, we'll take everything to be initially at rest. What we're going to look for is the acceleration of each of the blocks, and how long does it take this red block right here to hit the ground and fall the 24 centimeters, or 0.24 meters. Notice we're going to have to verify that, in fact, this block right here is heavy enough to fall down against the weight of the second block right here, the blue one. And we're going to solve this problem, again, using the exact same procedure we have used before. So we're going to start by drawing a free body diagram. And again, we're going to take the pulley to be massless and frictionless, so we do not need to draw a free body diagram of the pulley. You only need to draw free body diagrams of the two blocks. So take a few minutes and draw the free body diagram for both of them. Okay, free body diagrams. We're going to ignore air resistance, and again, we'll assume the velocities will be small enough we can neglect them. We're also told the surfaces are frictionless, so we do not need to worry about friction. So these are the forces we need to worry about: weight, normal, and tension. So we have the weight of the blue block, which is capital Mg, and the weight of the red block, which is little mg. And again, make sure that this mass is different from that mass because these two weights are not the same. We have the normal force because the blue block is sitting on a ramp, and the normal force is perpendicular to the surface of the ramp. It is not vertically up. And then we have the tension of the string acting on the blue block and the tension of the string acting on the red block. And those are all the forces, because that completes our little checklist. The next thing we want to do is pick an inertial frame of reference to describe the motion of the objects. Now, as I have noted past, that we don't need to have the same frame of reference for both objects. And it is always best to align the frames of reference relative to the direction the objects are going. The blue block right here will be moving up the ramp at an angle of theta. The red block will be falling vertically down. So the two accelerations are not going to be in the same direction. And what we can do is use one frame of reference to describe the red block and another frame of reference to describe the blue block. So what we're going to do is take one frame of reference, we'll call that frame of reference number 1, and we'll align the x-axis with the incline. And we'll use a second frame of reference, and we'll align the axes vertically and horizontally and use that to describe the second block, the red one. We'll call that frame of reference number 2. So we're going to apply F equals ma to the blue block in one set of axes, and we'll use a different set of axes to describe F equals ma on the red block. Both of these frames of reference will be attached to the ground, so both will be inertial frames of reference. But they need not be exactly the same. So we use one frame of reference for the blue block and another one for the red block. Now, next step is to use these two frames of reference to apply F equals ma. So take a few minutes and first just apply F equals ma to the first block, the blue block, and then write down the sum of the forces in the x and the y direction. Okay, for the block on the ramp, again, we're just reading these straight off the diagram. So we have, in the x direction, which is along the ramp, we have the tension minus one of the components of gravity. And remember, when we did the ramp, this right here is the angle theta. This right here is also the angle theta. So we have t minus mg sine theta. That equals the mass of this object times its acceleration. I'll call its acceleration capital A. In the y direction, we have the normal force minus mg cosine theta, which is the other component of the weight. Now what I want you to do is, again, take a few minutes and draw this and write the same equations for the red block, the second one, using the second frame of reference, vertical and horizontal. Well, here the block off the ramp X direction is very easy. There are no forces, so the net force is 0. Here we have tension minus its weight, and the tension is acting vertically up along the y-axis, weight acting vertically down along the y-axis, so it's T minus mg equals small m times small a. So this acceleration, capital A, is the acceleration of the blue block, and the small a is the acceleration of the red block. Now we need to note first that two of these equations, actually this one right here and this one, which is of course kind of irrelevant, are actually not needed because we do not need to find the normal force because we're not using any frictional forces. So we really don't need this second equation right here. All we need is the first one right here and the last one right there. Okay, next we need to concern ourselves with the constraints in the problem. You don't have to worry about force laws because we're not worrying about friction. Again, like before, we'll assume the rope is not going to stretch, so that for every centimeter this one moves up the ramp, the red block must move down 1 centimeter so the length of the rope doesn't change. And it must do it in the same amount of time, which means the velocity of this must be related to the velocity of that, so the speeds are equal in magnitude. And just as before, we'll find out that the magnitudes of the acceleration must be equal. Now here we have to note the sign convention we've already adopted. Up the ramp will be positive, and vertically up is positive. If the blue block moves up the ramp in the positive x direction, then the red block must move down vertically in the y direction. So therefore, the acceleration of the red block must be negative and the acceleration of the blue block must be positive, so that accelerations are equal in magnitude but opposite in direction. So little a equals minus capital A. And there's our last equation. So now we can collect our equations together. This is the first equation, the x component of the block on the ramp. This is the second, or the y equation, for the block hanging off the ramp. And this is how the two accelerations must be related by the rope. So take a few minutes and calculate the answer for the acceleration. Okay, you take all these equations, combine them together. This is the resulting expression. We plug in the relevant values and we find the acceleration is minus 7.57 meters per second squared. And that's part of what we were looking for. We also want to find out is the time it takes the red block to hit the ground. And that's a kinematics problem once we have found the acceleration. So we're given the initial velocity, everything starts at rest. We just calculated the acceleration using Newton's second law. We were told the initial position is a given height above the ground, which was the 0.24 meters, and we want to land on the ground, so we know our final position is 0. And we want to find the time that takes. So take a moment and ask yourself, which one of these 4 kinematics equations do we want to use? Well, here we probably want to use equation number 1 because effectively we know where we're starting out, 24 centimeters above the ground. We're going to end up on the ground. We know our initial velocity is 0. We calculated using Newton's second law what our acceleration is, so the only remaining unknown in this equation is the time t, which we can then calculate. And the time turns out to be a little less than 0.8 of a second. So that's our final answer. And again, we want to ask ourselves, basically, does this make sense? Well, first, the acceleration for A should have the units of meters per second squared, and it does, because it has the same units as g. And it is negative, so it is falling down, and that's good. The expression is based on the difference between capital M sine theta and little m. And what we want is this little m to be heavy enough to basically overcome the weight of the second mass. And here it is, because m sine theta is less than a little m. So the red block will in fact fall down. And that makes sense. So we are done.